and you'll tell us about global mirror symmetry.
Well, thank the organizer for put up this nice conference and also give me an opportunity to speak here. So my title here, this word global, is a long-standing word. It's a little bit confusing what I mean. So first, first part of my talk, I'm going to explain what I mean. This word global. Then I will sort of summarize a conjectural physical package actually developed here by Vafa and other physicists. Also was spoke about this morning by Clem. Then I will sort of sketch the approach to sort of construct this physical package rigorously for hypersurface, collaborative hypersurface of like weak projective space. Then towards the end, I will tell you a little bit sort of unexpected bonus we obtained by this construction. So let me first tell you what I meant for the global. This word global here. So then, okay, now I have to tell you what I mean local. So here, first of all, the local here does not mean mirror symmetry or local collaborative manifold. Okay, otherwise I wouldn't talk about this here. So what I mean for local, let me sort of first summarize, go a little bit, explain a little bit in a sort of simplest language what is the mirror symmetry. So sort of mirror symmetry is you start from a collaborative sweeper. Then what you want is you want to associate another collaborative sweeper. In the process, you sort of interchange A model with B model. Kind of information contained in A model are the sort of Cater structure. Then you want to sort of map to sort of complex structure. Then if you go, there's a whole list. The next on the list is the Jena zero Gomolten invariance that is mapped to the periods. The sort of famous example of this correspondence is a so-called quintet collaborative sweeper. Here, Si is defined by this degree 5 polynomial in CP4. Then its mirror has been well understood by Placer, by Green and Placer. This is a family. This is what I want to emphasize here. This is not a single collaborative sweeper. Actually, it's a family of collaborative sweeper defined by this equation, where the parameter is this psi here. Also model, they modify to the third power. So now, if you go down to this list, then the Cater structure here is the parameter is a Cater class. This even in the Cater cone. Then on the complex structure, the parameter is a psi. This actually living in the puncture P1 is a CP1 model 3 points 0, 1, and infinity. You can calculate the pi 1, for example. The pi 1 with this guy is non-trivial. The pi 1 of a cone, of course, is trivial. So you immediately find a counterexample for mirror symmetry. So there's no way you can match Cater cone to this moduli of a complex structure. Then, okay, so of course, physicists know this in the beginning. This is not something new. What do people do 20 years ago is I sort of treat it as a sort of temporary solution of the time. Is you try to restrict the sort of B side to a local neighborhood of particular points. In this case, psi equal infinity. This point actually has a name is called large complex structure limit. That's what I mean local. It means you only consider a neighborhood on the B model side. So that's what this local means. Now, for 20 years now, we have been studying this version. Now it seems the good time we try to sort of restore the global structure of mirror symmetry. Global means here is I'm going to allow the psi kind of move around in the entire modular space. I don't want to just restrict myself in the neighborhood of a large complex structure limit. Well, you can say, I'm pretty happy just study near this point. Why? I don't want to make my life unnecessarily more complicated. So let me just tell you a little bit about the benefit you're going to derive out of here. The one benefit is a computing high genus Gomolten invariance, for example, the quintet sweeper, where two talk in the morning also mentioned about this. Now there's a physical computation up to genus 51 that uses the global structure on B model side. You cannot get those results just by restricting yourself in the neighborhood of a large complex structure limit. Then other application, certainly mathematician will love is building is about modularity of Gomolten invariance. So that will find some connection to number theory, which Gomolten theory certainly will love to do that. Then also other application is you can pull something called Landau-Ginzburg-Calabi correspondence. This is a well-known sort of correspondence in physics. Now we can also try to do this in mathematics. Okay, so that's first of all that's what this word means. Global here means I'm going to move around on the entire B model modular space. All right, so now let me tell you what the physicists actually was considered this question already more than 10 years ago. So let me tell you what is a sort of physical package they have over there. So to explain this physical package, let me first tell you what is a B model, so the genus 0 B model invariance. That's basically corresponding to the periods. Instead, to explain the Calabi swivel, let me sort of go down to one dimension. There, everything is very classical. So this is a toy model. Now I'm going to go down to one dimension. Here, I go from 5 to 3. You see the formal equation are exactly the same, except I switch with 5 with 3. Now, once you do that, then this is an elliptic curve. Again, the moduli of elliptic curve is a P1 modular 3 points with 0, 1, infinity. Now, what is the periods? Well, the periods is this. You say, since this is a sort of Calabian manifold, there's a homomorphic 1, 0 form. For 3, 4, you're going to have a homomorphic 3, 0 form because like H1, 0 here is C. So for each side, you choose a homomorphic 1, 0 form. If you do this carefully, this can be chosen in such a way, kind of very holomorphically, according to the parameter. Then, well, this choice is not unique. The other choice corresponding to you multiply by some kind of homomorphic function in front of this. So this has been well understood. The next step so you have this Calabi 1, 0 form. Now to compute the periods, you also need to consider the so-called one cycle. That's a H1 of elliptic curve. This case, H1 has a symplectic basis because the intersection form here is a skew symmetry. So you can choose a basis AB with the property A squared B squared equal to 0, AB and BA equal 1, BA equal to minus 1. When you change basis, then you have this matrix in SL2Z. Now, periods is just an integral of this Calabi 1, 0 form against the cycle. So you have two periods, Q and P. Now, when you vary the psi, so this depends on the psi, this is going to be a multi-value function of the psi over P1 take up 3 points. Then as we know, in the theory of elliptic curve, if you take a ratio of two periods, this is going to be independent of a choice of psi, right? Because you have a real scale psi that has been crossed out when you take a ratio. Then this is a point upper half plane. So this is sort of modular parameter of elliptic curve. Let me just also remind you, this is going to be the relation between upper half plane and your original complement of the 1, 0 infinity in P1. This is a universal cover of this guy. Then you can sort of move around this 0, 1 infinity. That gives you some kind of modular group. In this case, can be identified with the subgroup of SL2Z. And turns out it's this so-called gamma 3. Then the general 0 Goldman invariance can be thought as a correspondence between sort of Killer parameter and the periods of psi near psi equal infinity with a spatial choice of the basis. Then that can be translated into, say, corresponding to a neighborhood of tau equal to I infinity at this point. So that's using this modular coordinates, and this is corresponding to this tau equal to I infinity. All right, so that's about elliptic curve. So now let's go back to swivel. There, the picture is almost the same. So that's a B model of a quintet swivel. And there, I will explain to you, the moduli is a complement of 0, 1 infinity. But this is again covered by upper half plane. So you can use the coordinates in upper half plane as your sort of modular coordinates. Then the main difference here is this modular group is no longer in the subgroup of SL2Z, rather in the SP2Z, because the H3 here is a 4-dimensional, rank 4, not instead rank 2. Then so this local mirror symmetry I talk about would be a statement. Say the general zero homomorphic mirror quintet can be identified with the periods near this point tau equal to I infinity. This is called large complex structure limit. This version of a local mirror symmetry has been proved in the 90s by Kevin Tao and Liu Yao. Here, our interest is two aspects. First, we want to understand what happened for the high genus homomorphic events. Also, what happened for the sort of global property of a homomorphic function, not just a number. We actually want to sum up as a function, see what kind of property that function is going to have. All right, so now let me tell you what sort of physicists expect the property you're going to have here. So that's what I meant. This conjectural. Okay, I guess for my physics friend, I'm sorry I call them conjectural physical package. Yeah. This physical package consists of two parts. It was first developed by BCUV in the middle 90s. This one part is a sort of a global property. There are several. Let me just sort of summarize what I expect. Then first, what they say is there should exist a globally defined so-called B model genus G homomorphic function. But what is interesting is this function is not holomorphic. First of all, it's defined for all the tau. Also, more importantly, this is not holomorphic. So if you are only calculating homomorphic events, you always get some kind of holomorphic quantity just by definition, because it's defined as a power series. So what is kind of surprising for us is that they expect something non-holomorphic. Then the second property is this is modular events. Just follow from the fact this is sort of globally defined. If you act by element or modular group, and then there's some kind of automorphic factor come out. This kind of Riemannian automorphic form in number theory. This is not a holomorphic, so you can take the derivative for the tau bar. Then you have a beautiful equation. This is called holomorphic anomaly equation. Already talked about by Albrecht Klemm in the morning. So this equation as a form is you differentiate it FGB with a tau bar. This can be expressed universally in terms of same general function with smaller genus. Well, in the Klemm's talk, he was talking about direct integration of homomorphic anomaly equation. And turns out they already solved this equation. This, in some sense, is equivalent to this function has following expansion, basically. It can be has a finite expansion in terms of the parameter imaginary tau. Well, if you are number theorist, that sort of reminds you the definition of so-called quasi-modular form. So that's where sort of number theory can come in. All right, so that's so you expect you have this FBG tau bar satisfy those global properties. Now the second part of package is the spatial limit. So that sort of consists of a series of sort of mirror conjecture. So now on the B model side, you look at sort of those spatial points. I already mentioned about one point is near tau equal to I infinity. This point should mirror to the homomorphic invariance of a mirror manifold. So that was a sort of original mirror symmetry or the local mirror symmetry I was referred to. Then there are some other spatial points. For the quintet threefold, you have 3 points, 0, 1, infinity. We just talk about infinity. Then there's other points like near psi equal to 0. Then this also is expected to mirror to a different kind of theory. It's called Landau-Ginzburg theory. So I refer to this as the Calabi-Yau to Landau-Ginzburg mirror symmetry. Then near this other point, psi equal to infinity, that's the so-called a conical limit. That is expected to mirror to some kind of matrix model. Well, that's only for quintet threefold. If you for other examples, there might be some other limit as well. Okay. Now let me just tell you what they can do. They are actually pretty amazing. The Albrecht group, what they do is they are assuming. So, from mathematical perspective, you are assuming the existence of such a package. then you study also some general property of a spatial limit. There's no explicit calculation you need to do. Just from this, then they have a striking computation of Goldman invariance for genus up to 51. Yeah. For us as a mathematician, we has been working very hard for 20 years. So we can only done for genus 0 and genus 1. Yeah. So it's kind of embarrassing for mathematicians. Yeah. Well, so that's why we want to understand this. So say, can we really put this package into mathematics? Then we can also compute up to genus 51 or even more. So the goal of a remaining talk is I want to sort of describe a approach. Is a mathematical construction of a Bob package for hypersurface. Well, most of the step I'm going to reduce the approach to some sort of technical step. The most of the step in the general situation is still conjecture in this moment. So if you're interested, work on that. But we can actually prove some theorem in dimension 1, which actually give you all the general feature of a arbitrary dimension. But the technically speaking is easier. Well, even in that case, we get something very interesting. All right. So the starting points of my approach is actually I understanding. So let me put back this transparency here. Even for, as I say, for quintet, for mirror quintet, we have a spatial swing limit. It's a infinity, 0, and 1, right? So we have been sort of studying this infinite limit for 20 years. Then what happened is last 4 years, we actually managed to understand a second limit. That's really the whole story started. So this the second limit, we sort of managed to construct a theory for that. Was originally actually a proposal written, then worked out by Fan, Jarvis, and myself in 2007. So this this new theory is a Landau-Ginzburg theory. The basic data into the theory is a so-called superpotential. In this case, is a long-degenerate quasi-homogeneous polynomial. The second piece of data is a finite abelian symmetry group here. Then this new theory is very much like Goldman theory. Instead, you solve the Debye equation. You solve this what I call Witten equation. This was proposed by Witten 20 years ago in 91. So we sort of spent about 7 years trying to solve this equation. Finally, we managed to solve them and build up a theory. Then this theory, as I say, is very much like a Goldman theory. For mathematicians, this is like a 2D gravity. Is based on modular space of curve, satisfies all the axioms of Goldman invariance. One advantage for this new limit is this is much easier to compute. For example, with the ADE elliptic singularity, with the genus 0 quintet, this whole list is kind of expanding very quickly. I should mention also here is this generalization for this has been working intensively by the group here in Penn. So unfortunately, I don't have time to talk about this. Otherwise, it will be a completely different type of talk. All right. So that's a sort of starting points of my new approach. Actually, all the idea is coming out of this studying this so-called Landau-Ginzburg model. Now, let me switch back to this general property here. So what happened for one? Namely, how do we build a rigorous theory for this FG tau bar? Particularly, I wanted them to be non-holomorphic and also satisfy kind of properties physicists expect. Well, this is a hard problem. Recently, there's a paper by Costello Lee. They work out a version for complex torus. I think Kevin probably is going to talk about this in the talk. So yeah, please attend his talk. This is something very interesting happening here. The approach I'm going to talk about here is works for hypersurface, such as a quintet waveform. So particular kind of example we have is in the quintet waveform. The sort of key observation for my approach is this. So when you have a difficult problem, you don't know how to do it. The one way to do them is embed them into some larger problem, and try to solve the larger problem. So sometimes it's easier to solve larger problem. So here, what happens is we can embed this Calabi-Yau deformation into a larger deformation by adding some extra parameter. So for example, for this elliptic curve, you originally have the side parameter. Now I'm going to add a bunch of other parameters, T0, T1, T2, T3, T4, T5, T6. Added 6 more parameter or 7 more parameter. Well, I didn't add this parameter randomly. This corresponding to something called mini-universal deformation or singularity for this Fermat polynomial. All right. So originally I want to only study the deformation Calabi-Yau. Now I'm telling you I want to study for this much larger deformation. So what I meant for that? So what is B-model theory for that? Well, it's so let me first tell you a sort of kind of baby B model, which is basically wrong, but give you kind of general idea how things going on. All right, so this B model actually is something that has been studied by mathematicians for quite a long time. So you take a polynomial, say there's a Fermat cubic. Then you can define an object called Mueller ring, or in some other context, you call local algebra or Jacobian ring. The simple name for that this basically is a sort of polynomial ring modeled by so-called Jacobian ideal, which consists of a partial derivative of this W here. So this case would be just like a x1 squared, x2 squared, and x3 squared. You can enumerate the generator for this Mueller ring. Is given by 1, x1, x2, x3, x1 times x2, x1 times x3, x2 times x3, x1, x2, x3. So you count how many you have, you get 8. So that's why I have this x4 7 parameter total give you 8 parameters. So this is a 8-dimensional deformation space. Then the sort of mini-universal deformation of this singularity just is you deform this singularity by the basis from this Mueller ring here. So you write them out. The Calabi-Yau deformation corresponding to this factor. So I particularly single out this guy, put a sigma here. Then you have some other extra parameter here. There are 7 of them because there are 7 different bases here. So my sort of B model, so now I have a much larger B model now. My B model parameter space is going to be 8-dimensional. They included the original sigma. Also, I have 7 other parameter I call Ti. So here, I want Ti to be small, but I'm going to allow sigma to deform arbitrarily because that's the original problem coming from out of a Calabi-Yau geometry. So here, actually, there's some kind of singular points here. Sigma cube is not supposed to be equal to 27. So that's a okay. So that's a B model, so modular space. Now the invariance, the first invariance you can extract associated with the B model modular space is this sort of deformed Mueller ring. You say again is a quotient of polynomial ring modeled by Jacobian ideal for this deformed polynomial. Again, this is sort of also 8-dimensional. So this actually gives you a family of Frobenius algebra. So what is a Frobenius algebra? Is a product together with a pairing. The pairing is defined by this residual pairing here. All right, so that's the sort of the kind of simplest kind of data you can obtain. Can be considered as sort of B model data. But in some sense, this is not really correct because let me make some remarks. All right, so the main advantage to including those this extra parameter Ti here is that if Ti is not 0 for generic value of Ti, then this function is a holomorphic Morse function. So that translated to a very nice statement about this Frobenius algebra is this Frobenius algebra is semi-simple. Namely, you can sort of diagonalize this algebra as a sum of a unipotent algebra here. That's it's called a semi-simple. That basically corresponds to the fact this is a Morse function. But there's a problem for this. The pairing is not flat. Well, for people who are not familiar to the subject, this may not sound a problem to you, but was a problem for people like 20 years ago. Try to get some kind of flat pairing. So how do they do this? Well, takes them quite a bit of work actually. So that's under the name of the sort of Saito and Giventhal theory. Then so the Saito series is corresponding to the general zero case. So what he was trying to do 20 or 30 years ago by Saito is he tried to do this, try to construct some kind of flat metric. His recipe is this: you look at the pairing where you do some kind of residue pairing here. You saw it's a volume form here, the dx1, dx2, dx3. So what his recipe is this is not flat because you should not choose a standard volume form. So what he want to do is he want to replace this sort of standard volume form by just multiplied by a factor. Is like he uses 1 over rho sigma. Then this is what he called primitive form. What he proved is once you multiply by some kind of, just by a factor, you can actually turn this into a flat metric, a flat pairing. Well, the Frobenius algebra together with a flat pairing is what people call Frobenius manifold. This is enough data for you to extract a general zero potential function, something like a general zero Gromov invariance. But I want to also emphasize here is this Frobenius manifold is semi-simple when Ti is not 0. But it's not semi-simple when Ti equal to 0. So that's kind of important. That's the reason the solar Calabi is kind of hard. Now when you move away from Calabi, you become something simpler because you are in a semi-simple situation. Then exactly in this situation where Ti is not 0, when this Frobenius manifold is semi-simple, then given tau define a higher genus potential function. His definition works precisely in the situation you will have a semi-simple Frobenius manifold. So here we do now we have suddenly have a definition of a high genus potential function when Ti is not 0. Well, okay. So that's the B model we're going to use. This genus 0 is going to be this F0 coming out of Frobenius manifold structure of Saito, and high genus this function defined by given tau. All right. Now let me. So since I mentioned about primitive forms, this is a kind of foundation for everything. So let me just tell you a little bit what do we know about primitive form. There's a particular factor here, 1 over rho. Well, they proved 30 years ago this always exists locally. So namely, you always have a sort of local Saito given tau theory. But if you're working in a very special situation, like ADE or elliptic singularity, the people also find out have an explicit formula for this factor here, rho here. But it's kind of hard to get an explicit formula in general situation. But one thing kind of nice, about this is since you are interested in the Calabi direction, right? So this is what people call marginal deformation. This actually is related to the periods. Yeah. So one thing good about this is since you say we want to get some kind of global theory by vary the psi globally, so we need to get some kind of global theory, not just local theory. The way we're going to do that is by relating them to the periods, since we know very well how to vary the periods globally. So this so we need some kind of global Saito given tau theory. Right now is underdeveloped by my postdoc Milanov and myself. So we have not yet have a theory in a higher dimension. All right. So now let me tell you what we do know. That's a dimension 1. There we can prove everything. Also, this even in dimension 1, this already reflects all the general features of this approach. So okay, the starting point is is periods. So as what Saito already know is there's a primitive form. This factor in front of volume form is basically a period. So namely can be written as an integral of a Calabi 1 form against a cycle. Also, let me also remind you, if the ratio of periods, since a elliptic curve has you choose a sympathetic basis A and B, you take a ratio of 2 periods. This is a modular coordinates of my elliptic curve. Then one thing kind of nice about here is you can also consider so-called flat coordinates along the marginal direction. It turns out this is determined by this ratio here. So you give one period, one cycle, well, that will determine primitive form. You have a dual cycle together. They also fix the flat coordinates along the marginal direction. Now, okay, so now by B model parameter space now, for the real B model parameter space, it's not a sigma, rather it's a Ti and a tau, and there's tau here. This modular coordinates tau. Tau is going to be in upper half plane. Again, relation between this and my original moduli is this is a universal cover. This is a map tau to the sigma here. So here's a picture here. So if you set a Ti equal to 0, you're going back to sort of Calabi deformation. Then the Ti is some kind of germ around the Calabi direction. Now let me sort of summarize what we know. For Ti and tau, any in T and tau, as long as for any in T and tau, you always have a Frobenius manifold structure, so that will give you F0. But when Ti is not 0, that's the semi-simple situation. This will have a definition of a high genus potential function. They're all holomorphic with respect to Ti and tau. Now, well, remember, as I said, physics package needed to be non-holomorphic. We don't want a Samson holomorphic. This is kind of rare situation. You don't want a Samson holomorphic. There's a good reason you don't want just a holomorphic object. That's sort of explained by following a theorem. This is sort of non-modular invariance theorem. This kind of is basically described by you actually sum them up, all the Fg to this sort of total descendant potential function. Now you try to calculate what happens if I apply an element of modular monodromy group. We can actually calculate them. And turns out the relation is given by this sort of x high. This is a differential operator defined out of H. You get some kind of complicated relation here. In particular, this holomorphic object is not modular. So from this sort of point of view, the reason is clear. Why you want something non-holomorphic? Because the holomorphic one is not modular. Then what's next is we find for us is kind of a magic trick. We find an explicit way to complete this to something non-holomorphic. This has a formula, has interpretation as expansion of this parameter here, imaginary tau to some minus j, where this coefficient here is a holomorphic object. This can be defined by a Feynman diagonal expansion using my original Fg. I should say this is completely motivated by Clem's work.
How is the original Fg defined?
Oh, so original Fg is the F0 is given by Saito's Frobenius manifold structure. Then higher Fg is defined by given tau on a semi-simple loci for Ti non-zero. Yeah, I will talk about that. What happened when Ti equal to 0? Because the slides were interested actually is Ti equal to 0. So right now I'm still working in the regime where Ti is not 0. So I sort of complete them to something non-holomorphic. For number theories, they should remind you of the definition of a almost homomorphic form. They have this kind of expansion here, but that's a particular kind of parameter. Then, as I say, the physicists already work out the solution for homomorphic anomaly equation is basically the solution for homomorphic anomaly equation is precisely you're going to have some kind of expansion like this. So once you write it like this, then it's pretty trivial to check this satisfies homomorphic anomaly equation. Then what is the difficult part is check this completion is modular. So that's another theorem. this is really the kind of only theorem. It's a this anti-homomorphic completion is modular event. This again is a calculation. Now I should come back to talk about this issue here. Ti is not 0 because the regime we're interested in precisely is Ti equal to 0. So now let me assume this can be extended to Ti equal to 0. Then you can just take your or desired object would be just you say the Ti equal to 0. Well, unfortunately, this is somewhat a difficult problem for this given top function. Then, well, let me. I'm gonna tell you how to talk about that, how to solve that issue just in next transparencies. So first of all, okay, assuming this, you can extend them to Ti equal to 0. Then there are sort of two nice corollary. You say now you expand this and Ti equal to 0, namely you expand as a power series of Ti where coefficient is a function of tau. This will actually give you a sort of classical modular form, classical almost homomorphic modular form, almost homomorphic form. So this is a direct connection to number theories. Then again, if I can say the Ti equal to 0, then again this will satisfy homomorphic anomaly equation. So this will be sort of desired object you wanted. But still, I'm sort of based on this sort of difficult this assumption which is not so easy to prove. Namely, you can extend it given the function to Ti equal to 0. All right. So how do we resolve that issue? Well, there turns out something kind of beautiful happening here. This is sort of part 5. Part 4 of my talk is this unexpected bonus I'm talking about. Is this larger function with a variable Ti actually also has its own mirror. So what is the mirror here? Well, it's this quotient of elliptic curve. So originally, I'm sort of started from try to study this cubic, and then turns out I sort of embedded this larger theory. This larger theory again has a mirror. This mirror is the quotient of this cubic elliptic curve by Z3 multiplied by Z3 squared. This has a more common interpretation as an orbit for P1, namely is a sphere with 3 orbital points where local isotropic group is Z3, Z-3 here. Then this also have some kind of Landau-Ginzburg dual. Is just a W, superpolynomial W with this group here. Then to resolve that issue, there's a theorem of my students, Kravitz and Sen. So what do they prove is they prove this sort of this local this spatial limit problem. Is a near tau equal to 0. This actually equal to this Landau-Ginzburg theory I was talking about. But since we know this Landau-Ginzburg theory can be extended to Ti equal to 0, so that solves the extension problem. So you identify with them with something which can be extended already. I'm almost done here. Now, the second theorem is that when tau equal to infinity, they identify this with the common theory of this orbit for P1. Under this very interesting substitution here, Q equal to e to the 2 pi tau over 3. Not only this, they can also do this. They also prove this same thing holds for two other orbit for P1. With the weights 244 and 236. All right. Now, in the last minute, so this is let me give you some bonus. Then this you imply the common theory of those 3 orbit for P1 are quasi-modular. As I said in the beginning, this is something very much wanted by mathematicians. Build a connection to number theories. Then other consequences they establish the Landau-Ginzburg-Calabi correspondence, again for this example, for all the genus. This is a kind of first example of such type. Well, what happened for our original problem? Well, this mathematically is sort of less important results. Since you restrict back to Ti equal to 0, of course, you're going to pull elliptic curve, common theory elliptic curve also are quasi-modular. But this is already known by Okenkopf and Pendleton using different method about 10 years ago. All right, let's start here.
Take the Landau-Ginzburg theory that you studied.
Right.
That's mirrored to P2 not
Yeah.
where the local Z2, there are 3 fixed points on Z3, and each one has 2 elements. And then there's a Taylor class of identity, which uses 2 more gives you the 8 class of your complement.
Actually, look, also because Zima 3, not Zima 2. It's not a T2.
Z3, I said.
Oh, Z3, yeah. Okay.
Maybe I meant T2 mod Z3, you get 3 fixed points, and those are the 6 plus 2, which is your 8.
That's right.
Now, genus 0, I would have no problem going to the limit value to 0 giving you the same as right. But higher genus, you have these twisted fields wrapping around the non-trivial cycles of the genus G curve. It's not going to be the physical problem of T2 mod Z3 is not equivalent to T2 because you have twisted sectors.
That you raise a very interesting question. Yes, when you restrict back to Calabi-Yau situation, right? That's the question you're asking, right? Do I really get it to Calabi-Yau theory? That's a very good question. It turns out in one dimension, you need to prove this. In one dimension, indeed, you obtain the original Calabi-Yau theory. In 2 dimensions, the original Calabi-Yau theory actually equal to 0. The K3 theory is 0, but this orbital theory is non-trivial. Okay. Yeah. So, yeah. Okay. So I misunderstood your problem. Yes. The statement is if you choose your insertion from Calabi-Yau, then you should obtain the Calabi-Yau theory. You sort of restrict your function on sub-slides, then that should give you. That's the answer I was trying to give you in the beginning. You say, yes, there's an issue there. If you take this insertion just from Calabi-Yau, you have some extra insertion, this twisted insertion from orbital, right? If you just take insertion from Calabi-Yau sector, you can compute the invariance. That invariant in dimension 1 turns out to be is invariant of elliptic curve. But in higher dimension, generally there are some of 2 terms. There's one term is coming from Calabi-Yau. You may have some other term, some other correction term. That's why I stopped claiming this in higher dimension. So yes, there are some work to do over there to separate out this extra contribution. Yeah.
But I think what I'm trying to point out is that this separate thing out might be a key obstruction to your program. Namely, the idea of trying to extend the moduli space has a completely different symmetries that is precluded by the
Could be.
For example, having these factorization properties like the homomorphic anomaly will fail because you have to have these extra segments inserted by hand, which you want to preclude. So it won't factorize.
Actually, one thing I want to use is what you say. Try to use this fact there's a difference when you use the homomorphic anomaly equation to try to sort them out. But of course, as I said, there's this issue there. Yeah. But nevertheless, this does give you a Gomorrhian theory of this orbital Calabi-Yau manifold, which is interesting of its own right. Particularly, for example, like K3, there's no non-trivial Gomorrhian invariance, but this orbital K3 has very interesting Gomorrhian invariance. Yeah. This is really only for quotient of elliptic curve. Yeah, you have to do some extra work to get a original non-Lagrange Calabi-Yau correspondence. This is the issue the Kuhlmann raised. Yeah, you have to work on that.